This is a nice exercise in analysis. The task is the following. Prove that the set omega, which is the closed interval 0, 1, is uncountable. So omega is x such that x is between 0 and 1, including the boundary values. This set, the boundary of the omega has the value 0 and 1. The closure of the set is the set a union with a boundary. So that's going to be x is going to be omega union the boundary of omega. And that is going to be just that one, which is equal to omega. So the closure of omega is equal to omega, which means that omega is a closed set. Also, omega is a bounded set. So omega is a compact set. This set has very interesting properties. This interval 0, 1 is very usually encountered in analysis. So how to prove that set omega is uncountable? We do it in the following way. Proof. Let's assume that omega is countable and start listing numbers. Okay, we are going to use the Cantor process here. We have some decimal representation A11, A12, A13, A14, and etc. A21, A22, A23, A24. Let's say that we can list all these numbers in the set 0, 1. And we keep going with this process, A and 1, A and 2, A and 3, A and 4, and so on. Now let's look at this. Let's look at A11, A22, A33, A44, all these diagonal elements. And let's take 0 dot B1, B2, B3, etc., where B1 is A11, B2 is A22, B3 is A33, B4 equals A44. And let's have a look at this number here. This is not included in the list. Okay? So we start by assuming that we can count all the numbers between 0, 1. We have this representation, we have this representation, that. But this is not included in the list that we wrote down. So since we have this outside the list, it means that omega is not countable. This process via Cantor Diagonalization process. This process is called the Cantor Diagonalization process. So it's basically a proof by contradiction, we start listing all the elements in this set by decimal representations, and we see that we have this digit in the diagonal, and we can use this digit to write another number here, but we can see that this number is not included in the above list. If we keep listing these numbers, we keep listing, this one is not included, so it means that we cannot count all the numbers in the set omega, and the proof is complete. Is a very famous proof, very famous approach by Cantor to prove the uncountability of closed domain 0, 1.